Hello, everyone. Louis Kirsch here. I'm glad to have you all here. So every year at NeurIPS, there's plenty of researchers presenting new reinforcement learning algorithm at the conference. And the question is, can we automate this process of discovering new reinforcement learning algorithms automatically? And in this talk, I want to investigate whether we can find in-context learning agents who can actually implement very general purpose reinforcement learning algorithms. So if you think about meta learning, it usually excels in adaptation to unseen but similar tasks. So you might have a bunch of grid worlds where you can train on an environment distribution and then generalize to a very different grid world environment. But perhaps not to completely different environment, like here in this ProgGen environment distribution, where you would train on the ProgGen environment distribution and then generalize to different other tasks like different visualizations or physical constants in these ProgGen environments. Or you might have a third environment with robotics here, where you train over a distribution with different morphologies of robots and different goals. But really, what we might be interested in here is a generalization across all of these environments, and what I call this general purpose meta learning. So we want to train an agent that can effectively generalize, so effectively in context learn and act across all of these environments. So both on the environments it was trained on, So both on the environment that it was trained on, as well as new environments that we haven't even seen in the training distribution, but are significantly different. There has been some prior work on this goal with gradient-based meta-learning, where we have essentially looked for new reinforcement learning algorithms similar to how humans would do it, in the sense that we have meta-learned objective functions that represent learning algorithms, and then at meta-test time, we would follow a gradient in order to implement learning in the agent. And there have been various works in this direction, just a few examples here on the slide. So in these works, essentially, we have a sort of gray box learning at meta-test time, where we are still using gradient descent to do learning, but we follow this meta-learned objective function that describes the reinforcement learning algorithm. Now, in this work, we want to do in-context meta-RL. So what does that mean? We don't want to even use gradients at meta-test time, but perhaps a completely different mechanism that is purely implemented in one black box neural network, like a transformer, an LSTM, or a fast-wave programmer. So what that looks like is like a policy where you condition on observation to generate an action, but you also condition on the transitions that the agent has seen, observations, actions, and rewards. And I want to highlight here that we're interested in learning from online from these previous transitions that the agent has seen, and not learning from demonstrations. The challenge with this is, while this approach is quite expressive, this policy is a very expressive parameterization, it's quite difficult to make it generalize. And in this paper, we want to investigate how to fix this. So we envisioned that if we had a really big task distribution, perhaps assembled or generated tasks, then if you could train across all of them, we would be able to find this very general purpose in-context learner. And in this paper, we want to take some first steps in this direction. We take inspiration from a previous paper from last year called General Purpose in Context Learners, and this was in supervised learning. And one key result in this paper was that we can transition between different kinds of learning algorithms implemented in a transformer the more tasks we see. So specifically here in this plot, I want to visualize these different phases a transformer goes through the more tasks we train on. On the x-axis is the number of tasks we train on, and on the y-axis is how much the agent is learning. We see that for few tasks, up to 2 to the 6 number of tasks, we just don't do any learning. And this actually corresponds to memorization. The transformer just memorizes what's happening in these tasks and directly solves them. And as we increase the number of tasks, we suddenly go to task identification, where we can do in-context learning on the tasks that we have trained on, but we don't generalize to completely different unseen tasks. And something interesting is happening if we increase the number of tasks even further to 2 to the 15 tasks, or above, where suddenly we can generalize to completely different image classification data sets here in this case. So can we do something similar in reinforcement learning? Instead of having this in-context supervised learner, where we condition on multiple examples, xi, yi here, and then this query point x tick to predict the respective class for it, y tick, we want to do this in RL. So we train on RL data where we have multiple transitions that we condition on that the agent has collected online, and some current state to predict an action for. And our recipe in this work to get to this strong generalization is to use offline meta training and augment the RL data in a way to get a really big task diversity. I want to highlight here that the meta training is offline, but we're actually learning an in-context learning agent that learns online from data as it interacts with the environment. So how does this work? First, we have a PPO data collection stage where we have some environment distribution of various environments, and we use PPO to collect a data set for these environments. So we start with some initial policy here that collects data. Then there's some PPO update. We get a bit of a better policy and so on. So this long trajectory of different policies that improve. And then we subsample this trajectory of policies to essentially get a trajectory that is shorter and it describes a learning process that is faster than PPO. And then finally, we would train on this subsample trajectory to imitate the learning process that we have in this data using a transformer. So the transformer conditions on all of these transitions to then first predict actions that are not so good, and then the more transitions it sees, it predicts actions that are better and better. Now, the key here is our augmentation technique, because we want a really diverse data set in order to show generalization. And we actually take a very strong augmentation approach here, where we randomly project observations and actions such that we can create many, many different environments in this data set that don't really look alike, but look very different from each other, and then train across all of them. So we always sample a new linear projection matrix to project our observations and a linear projection matrix to project our actions. And then on all of this augmented data, we do the training as we've just discussed it, and we get a new trained transformer where we fix the parameters, and now we only running it in inference mode, just auto-regressively sampling actions, getting the next transitions, predicting the next action, and so on. And this transformer, we're running it in inference mode, we could test on a new environment. So how does this work in practice? So here I want to first focus on a single environment to get some intuition. So we have some PPO trajectory here on a grid world environment, and then we train our transformer just on this one environment for now, and we see that we are more sample efficient than PPO. And similarly, on continuous control, we could do this in the end environment, where we're also now learning in context from interaction with the environment in this transformer. And I've discussed this gap to accelerate the interaction with the environment, so have a learning process that is faster than the original one from PPO. And as we increase the gap, we can also accelerate the kind of learning algorithm that is implemented in the transformer. Now we have these single environment cases here. What about the multiple environments and the generalization to completely different problems? So in this case, we wouldn't imagine Ant to generalize to, say, the Reacher environment or the carpool environment after we've just trained on Ant. So now we throw in our random projections that we've just discussed. So we collect data using PPO on Ant, we augment this data set, and then train our transformer on that. So here is our data collected from PPO, where we see that the more steps we have, PPO is doing some learning. But when we then run our transformer that we've trained on this data, we actually see it's more sample efficient and does some learning on the Ant environment. So this is the environment we've already trained on. Not too surprising that it implements learning on it. But we see that when we just test our transform and inference mode on other environments, that it also implements some learning, like on the Reacher environment or the carpool environment. And it also is more sample efficient than PPO. So in my eyes, this is an interesting demonstration that if we really get a broad task distribution, that we can get this generalization to different state spaces, action spaces, and dynamics, where an agent can learn just from interaction on these environments. Of course, these are early results. I think there are some important challenges that we have to work on in the future, like longer contexts. If you think about standard RL algorithms, they interact over hundreds of thousands of millions of interactions, and it's hard to fit into the context of a transformer. And then also the training dynamics sometimes are a bit difficult during meta training, and that's something we want to look into more. And in the far future, I'm envisioning that we can really assemble these big training distributions or devise environment generation procedures to get this really big breadth of environments that we can train our in-context learning agents on to really rediscover new reinforcement learning algorithms purely from data in context in black box models. And with that, I want to close my talk. Thank you very much.